Hello, this is an addendum to the Financial Computing 2 course that we just finished at the end of Mini 3. These are a few items that I didn't have time to get to that will help you in Professor Kramkov's FC3 course, namely the standard std: function, some specific algorithms, and I'm just going to briefly mention something called the unique pointer, which is somewhat similar to the shared pointer. Okay, so we've talked about some standard algorithms, such as the for each algorithm and the transform algorithm, and we've seen that you can pass function-like objects in to these standard algorithms as their final argument. And those function-like objects are then applied to the items in the, between the begin and up to but not including the end iterator. But suppose rather than calling a pre-existing algorithm, we needed to define an algorithm ourselves. How would we go about specifying the data type of a parameter, meaning provide some function-like thing here? Well, this is what std: function is for. To use it, we're going to include another header called functional, and you can see the gory details at this website. All right, so here's an example. I'm including IOStream and vector, and then I'm including functional so that I can use the std: function facility. I'm defining here my own simplified my for each algorithm. This is not as general as the standard for each algorithm, because this thing that I'm writing only works for vectors of integers. It does not work for arbitrary collection types. In my definition here, the first argument, bg, is the iterator for the beginning item in the vector. All right, its data type is iterator that is a member of the vector of int class. And likewise here I have my end iterator that is a member of the vector of int class. And here I have the function-like object that I want to be able to apply to each item in the range from begin up to but not including end. And the data type that I specify for this function-like object is function, which is a template data type, and then I provide the template arguments. The parentheses in here indicate that the thing that I need to pass has to be able to accept the function call argument, namely the open and close parentheses. What's passed in to this function-like object f is a reference to a particular int, and what's returned by this function-like object f is void or nothing. Okay, so assuming that the user, the application developer, has passed in a function-like object that satisfies these interface details, it can be called, it will be called with a reference to an int, and it will return void. Then here is a for loop that implements the gory details of stepping through this vector and invoking the function-like object f on each of the quote pointed to unquote objects within the vector. All right, and so in my code, that's exactly what I have right here. Now, to illustrate that this function template type does allow me to pass various kinds of specific function-like objects into the my-for-each algorithm, what I've first done is I've created an actual function named print that takes a reference to an int as its parameter and that returns void. And all this print function does is to display the current integer's value with a space after it. All right, then I'm creating a vector of integers, IV, with 3, 9, 12, and 4 as the values. I'm using my for each from the begin up to but not including end. And I'm invoking print as my proper type of function. You know, that's my function-like object. In this case, it is actually a function. And that's going to go through and print out each of the values one by one. In this next case, once again, I'm going through the vector from the beginning. From the beginning up to but not including the end. And in this case, I am using a lambda expression. The lambda expression will receive a reference to an int and will modify that int by subtracting 5 from it. And then I'm going to use an ordinary for loop to go back through and display the modified element values of that. Okay, and I have my print function definition here and my main function using my for each twice, once with an actual function and once with a lambda that provides a function-like object. Now let me compile and execute this code over here. Okay, so G++, the standard is C++20, and the name of the code file is funexample.cpp, and I want to create funexample as my executable code. And it worked. Cool. So no syntax errors. Compiler was happy with my use of function there. And I'm going to run this now. And it works. Okay. IV initially contains 4 items, 3, 9, 12, and 4. And that those values, 3, 9, 12, and 4, are displayed by, those values, 3, 9, 12, and 4, are displayed one by one by using the my-for-each algorithm with print as the actual function-like object to be invoked. And then the second my-for-each loop is using a lambda to subtract 5 from each item, and then I have a range for loop to display those things. And sure enough, each of the values in that second output is 5 less than the previous output. So 3 minus 5 is minus 2, 9 minus 5 is 4, etc. All right, so that is what function is about. We've talked about algorithms like for each, transform, and copy. And I also just showed you this long list of other standard functions that are available. You will want to go through the documentation and look up and practice with each of those available standard algorithms. I want to illustrate here a few that Professor Kramkov will be using. This is not obviously the entire list of everything he'll be using, but it's some anyway. We're going to start out by, well, first of all, we need to include the algorithm header to access most of the standard algorithms. I'm also going to include cstandard lib because I want to use the rand function to generate random integer values for my demonstration vector or vectors. srand is how I can set the seed for my random number generator so that if you execute this code, you'll get the same results that I do. All right, so here is my empty vector of ints called IV. I'm going to set my random seed to 0, and then I'm going to generate 10 random integer values ranging in value from 0 up to but not including 10, so from 0 to 9. Now, if I generate 10 random values in the range from 0 to 9, the odds are pretty high that I'm going to have some duplicates. And indeed I do. So here I'm using a range for loop to display what ended up in IV, and I happen to have gotten 033290826. And we can see just by glancing at this that there are duplicates. We've got 2 zeros, 2 3s, 2 2s, 2 6s. Well, one standard algorithm that's nice to know about is an algorithm called isSorted, which will simply return to you true or false depending on whether the collection is sorted or not. And by default, it's checked to see whether it's in ascending order. All right, so here is my vector. I'm going from the begin up to but not including the end. And of course, these values are not sorted in ascending order, so I ought to get false. And in fact, I do get false. Now, in order to see false rather than 0, I'm turning on my bool alpha manipulator. Okay, otherwise I would have gotten a 0 displayed as the integer equivalent for false. All right, well, so we're told that vector is not sorted. Here's another standard algorithm, sort, which by default will assume you want things sorted in, well, let me say non-descending order. We can't get strictly ascending here because we have duplicates. But when I use the standard sort algorithm, I get the results in non-descending order, 0, 0, 2, 2, 3, 3, 6, 6, 8, 9. All right? And now if I ask again, now if I ask again whether this thing is sorted, sorry, having trouble with my highlighter here. But of course now the vector is sorted and I get told that that's true. Let me show that code. All right, so here we have this code. We've created IV containing 10 random integers from 0 to 9. And I'm doing the isSorted test and getting false. Then I'm sorting and doing the isSorted test again and getting true. And I will run this whole thing a little bit later. Okay, here's a couple of other useful functions to know about, namely upper bound and lower bound. If you have a sorted collection, then upper bound between the beginning and less than the end, or one prior to the end, allows you to search for the location, the iterator within that collection for the lowest value that's greater than some upper bound. So here my upper bound is 3, and I want to get the lowest value that's greater than 3. That is, the upper bound on 3, and the lowest value that's greater than 3 is this 6 right here. All right, so I get back an iterator for that upper bound, if I display the value at that iterator, I should get a 6, and in fact I do get a 6. I can convert that iterator value to an integer subscript by subtracting the beginning iterator from the upper bound iterator. This will give me the integer offset in terms of elements between the beginning and the upper bound. All right, so the upper bound is the 6. Begin is pointing at this 0, if you will. And if I subtract that pointer to the 6 from the pointer to the first 0, I get 1, 2, 3, 4, 5, 6 as my index. To say that another way, if I probably should have done this in my code, but let me just add it here as another comment. What it means to say that the index is 6 is that if I say IV sub 6, I will get, and it's sort of an unfortunate coincidence, but IV sub 6 is the value 6, which of course is the lowest value that's greater than 3. Now, the lower bound within the same vector for 3 is the lowest value such that the value is greater than or equal to 3. Now, if I look at my sorted vector, the lowest value that is greater than or equal to 3 is this value right here. That value is greater than or equal to 3, okay? It happens to be 3. And it's the lowest value in this vector that is greater than or equal to 3. If I didn't say so before, that just reminded me to mention that, of course, the vector has to be sorted in ascending order for these upper bound and lower bound algorithms to do anything that makes sense. All right, and the index of that 3 is 0, 1, 2, 3, 4. In other words, IV sub 4 is going to be that particular 3. All right? So the value at that lower bound iterable happens to be 3. It might have been a 2. I'm sorry, it might have been greater than 3. It might have been like a 4 or a 5. And the index of that lower bound position in the vector is position sub 4. Okay. We also have a few numeric algorithms. These were not in that long list of algorithms that I briefly showed you. For example, we have an inner product algorithm, and we have an accumulate algorithm. Those are the only two that I'm going to demonstrate. There are lots of other numerical algorithms as well. All right, so for this purpose, I'm creating two test vectors, IV2 and IV3. IV2 has integer values 3040. IV3 has integer values 0108. And the inner product, or the dot product, is computed in the way that you would assume. It's the sum of the products of the elements of these two vectors. Now, I have to give the begin iterator and the end iterator of the first vector. For the second vector, I only have to give the begin, because the assumption is that that second vector must have at least as many items in it as the first vector does. If that second vector is too short, this thing will not work. It'll crash or do something bad. I also, in this inner product function, need to specify an initial value for the product. That initial value will just be added to the dot product between IV2 and IV3. So for my case, I want to use 0 as the initial value. Well, if we glance at these two vectors, 3040 and 0108, turns out these vectors are orthogonal to each other, and consequently, the dot product, when you compute the dot product or inner product of two orthogonal vectors, you're going to get 0, and 0 is exactly what we do get. All right, 3 times 0 plus 0 times 1 plus 4 times 0 plus 0 times 8. I could have been more clever about choosing less obviously orthogonal vectors, but those are pretty obviously orthogonal to each other. Now, on the other hand, here in this next use of inner product, I'm computing the inner product of just the one vector, IV2, with itself. Now, when you compute the dot product of a vector with itself, you get the square of the magnitude of that vector. And here I was kind of careful to choose easy numbers. We've got 3040. So that turns out to give me a 3, 4, 5 right triangle, and consequently the dot product is going to be 9 plus 0 plus 16 plus 0 is 25. All right. Okay, so those are just two quick examples of inner product. And then accumulate. Accumulate allows you to compute the some if you will, compounding binary mathematical operation over all of the values in some range in a collection. This time I've created a brand new vector just containing 1, 2, 3, 4. If you're a bowler, you know without even thinking about it that 1 plus 2 plus 3 plus 4 is 10. Well, if you're doing American bowling anyway. And if I say I want to accumulate from the begin up to but not including the end, starting with an initial value of 0, I compute that 0, my initial value, plus 1, 2, 3, 4 is the value 10. Okay? So summation is the default function that's applied when you use the accumulate numerical algorithm. But you can specify an alternative binary arithmetic operation to use instead. And this time, instead of using a lambda expression, I've chosen to remind you of the predefined binary operations, function-like binary operations that are available within the standard library. All right, so what I want to do here is to use the multiplies int function. This is the constructor that will create a multiplies int object. And because I'm multiplying a bunch of values together instead of adding a bunch of values together, I need to be careful to use 1 as my initial value. All right, and so the product of that initial 1 that I specified with the 4 values that are actually in IV4, 1, 2, 3, 4, well, that turns out to be just the initial value I specified, 1 times 4 factorial, which we know, or if we don't, you can compute it in your head pretty much right away. We know that that's 24. Okay? All right, and so, of course, in addition to adding and multiplying, you can use other kinds of binary operations with accumulate. Okay, so let me run this thing. Oh, by the way, I forgot to mention that. Oh, I guess I did remember to mention it. For these numeric algorithms, such as inner product and accumulate, you need to include the numeric header, which you can do Typically we would, I guess I did do that up at the top, but I did also, come on now, I did also put it in right down here. And remember that for standard headers, they are using it's funny. All right, now I've forgotten the term, but they are protecting themselves from being included multiple times. So including numeric twice is no problem. And here we go. So let me actually compile and run this thing now. This is my, let's see, G++. The standard that we're using is C++ 20. And this is algo examples. And the output is going to be algo examples. And I can run it. There we go. All right. So we start with an unsorted vector. We sort it. We discovered that the upper bound of 3 is this value 6, which is at index sub 6. And the lower bound of 3 is this first value 3, which is at the subscript 4. Now I've got my two orthogonal vectors, 3040 and 0108. So if I compute the inner product, I get a 0. If I compute the inner product of IV2 with itself, I get 9 plus 16 is 25. And here are what I get by accumulating 1, 2, 3, 4 as a sum and also as a product. And the only tricky thing there is you've got to remember to specify the correct initial value as the third argument in these cases. All right, well, finally, I'm just going to very briefly mention, we did talk about shared pointer, and we saw that we could have multiple copies of shared pointers, like we could have a single variable in our arithmetic expression tree, one variable that had multiple different shared pointers pointing to it. And it was only when the last of those shared pointers was out of scope that the single variable was deallocated. Unique pointer only allows you to have one unique pointer to a particular object, instead of being able to have multiple pointers to the same object. And you can create a unique pointer using make unique. So that's going to pop up in some examples. All right, well, I hope that was helpful. And take care.